Hello everyone, this lesson is about dynamic friction. Dynamic friction sometimes is called kinetic friction. You know what the friction is. When the two objects are rubbed against each other, there is an opposing force which is called friction. But dynamic friction is a specific case of that, when the two objects are in relative motion. What do I mean by that? Let's say this person is pulling the object on the ground and it is in motion. So the surfaces in contact are really rubbed against each other and are in relative motion. Necessarily, there is a normal force here, in this case equal to weight, but not always. Anyway, let's say it's 8 newtons. In this experiment, it turns out that the force you need to hold the object at a constant speed is 2 newtons. It's an example only. So I can infer here I have the same opposing force like 2 newtons. This 2 Newton force is called the dynamic friction. In the next experiment, I keep the same nature for the surfaces in contact, but maybe a larger box with the same type. So the nature of the surfaces in contact is kept the same, but the object is heavier. Let's say the normal force is doubled. Now, the same experiment will show that the dynamic friction is doubled. So if I double the normal force, here I see that the friction force also is doubled. How can I infer a formula for that? It's very easy. Let's say in the first experiment, the friction is a coefficient like 0.25 times the normal force. If I keep the same coefficient in the next experiment, I see that it is the same, just because the nature of the surfaces in contact is the same. Okay, how can I infer a general formula? Let's say the friction force is always a coefficient which is highly affected by the nature of the surfaces in contact multiplied by the normal force. So in general, the normal force is N, the dynamic friction is Ft against the motion, and then the dynamic friction is going to be a coefficient which is called coefficient of dynamic friction multiplied by the normal force. Keep in mind the normal force is not always equal to weight, but in this experiment, yes. We will go over different examples to cover all the cases. Look at this question. An object of mass 5 kg is pulled by a horizontal force of 45 newtons, as you see. Calculate the acceleration. G, the gravitational acceleration, is given as 10, and the dynamic coefficient of friction is 0.2. I just remind you that the coefficient of dynamic friction is not going to be always a coefficient less than 1, but mostly it's less than 1. Depends. Sometimes it's greater than 1, and it is not very unusual, but mostly you don't see a very big value, and it doesn't have any units. Okay. For having the acceleration here, we need all the forces acting on the object, the net force, because according to the Newton's second law, we need the net force to put it equal to ma. This is the acceleration, our goal. Horizontal net force acting on the object will not be only the 45. Also, there is a friction against that. To find that friction, we need first the normal force, because we know that the dynamic friction Ft is equal to mu d times the normal force. So to find the dynamic friction, first we need the normal force. How to find it? It's very easy. You see the object is not acted by any vertical force except mg. mg is downward 50y, because m times g, mass is 5, g is 10, so it seems to be 50 newton. Okay, I'll continue with the normal force. Normal force will be equal to that, because we believe that the object on this horizontal surface will not be accelerated vertically. The acceleration might be horizontal. If there is an acceleration, let's check it. 45 newton to the right, and then the dynamic friction leftward. The dynamic friction is supposed to be mu d times this 50. Mu d is 0.2, so it's 0.2 times 50. It seems to be 10. So the dynamic friction here is 10. So on the horizontal axis, I have a 45 rightward and a 10 leftward. So if I subtract them, I will have 35. So net force will be 45 minus 10. So it's 35. I put 35 equal to ma 5 times a. So acceleration is going to be 7 meter per second squared. It is not always an accelerated case. Sometimes if you apply a force equal to this friction, let's say it's 10, the object will move, can move actually in principle, but not in an accelerated motion. It's just a uniform motion. Anyway, for the time being, it's accelerated. Let's go to the next question. A mass of 2 kilograms is pulled by a 20 Newton force as shown in figure. As you see, this force is not horizontal and not vertical. It has a couple of components on horizontal axis, vertical axis. They are very important components for us. So before I continue, I should decompose this force. Okay, find the acceleration again. To have the acceleration, first of all, keep in mind that we should write F net again equals ma. On vertical axis, I'm really doubtful if the object is accelerated. We will check it, but most probably not. But in horizontal axis, it may have acceleration because the question is asking for. How to decompose this force? Sine of 53 degrees is given to be 0.8. For decomposing this force, I will have a horizontal component, let's say it's Fx, and a vertical component here, which is called Fy here. Fx is 20 times cosine of 53, because in this right triangle, as you see, Fx is the horizontal component. Actually, 20 is the hypotenuse of this right triangle, and Fx is the base of this triangle. So it's hypotenuse times cosine of 53. Fy accordingly will be 20 times sine of 53. So it's very easy. Let's check them again. Here, 20 times cosine of 53. If the sine of 53 is 0.8, so the cosine of 53 is going to be 0.6. So it's 20 times 0.6, and the vertical component is 20 times 0.8. So the horizontal component is going to be 12, and the vertical is 16. Now I can decompose this force. Okay, 12 and 16. On the other hand, you know that there is always a downward force of mg. Why mg is 20? Because mass is 2 and g is given to be 10. So it's 20. Anyway, vertically, I know that there is a 16 Newton of force and downward 20. There is a missing force here. Just with this 20 and this 16, the object will go to the ground. And I know that, at least in this case, the surface is strong enough to hold the object. So there might be a normal force like N to hold the object, not to let the object to penetrate to the ground. Okay, this normal force will just balance the vertical forces. I have a 16 Newton of force, and to cancel the 20, I need just 4. So the surface is smart enough to generate just a 4 Newton of force vertically upward as the normal force to hold the object. So the normal force is 4. But why am I so interested in this normal force? Because in Fnet, I know that there is a horizontal force of 12, and most probably a dynamic friction here, which is going to be subtracted from that 20, and I put them equal to ma. For finding the dynamic friction, I need the normal force. This is why at the beginning I decomposed that 20 Newton. Okay, how to find the Ft? It's very easy. Ft is going to be mu d times the normal force. Mu d is a half, and the normal force is 4. Half of 4 is 2. So easily I can say the friction is 2. Okay, on horizontal axis I see it's 12 and it's 2. So I should subtract them. 12 minus 2 is equal to ma. Mass of the object is 2 and acceleration here. So here 10 is equal to 2a, and the acceleration seems to be 5 meters per second squared. Vertically, the object is not going to be accelerated because the normal force and the component of 2 and 16 can easily cancel the weight. So the object just will accelerate in horizontal direction. Another example. A box of mass 3 kg is pushed to a wall by a horizontal force of 60 Newton, as shown in figure. You see, there is a horizontal force of 60 Newton and is holding the object on the wall. Anyway, calculate the acceleration of the mass. How can we find the acceleration? First of all, keep in mind that the wall is strong enough to hold the object. So in horizontal direction, more likely the object will not accelerate. Maybe the acceleration is vertical. But how? Here the coefficient of dynamic friction is given to be 0.2 and g is 10. Okay, first of all, let's say F is equal to ma, F net. F net in vertical direction, as in horizontal direction we don't have any acceleration, so vertically the object will be acted by some forces and it will accelerate. The downward force of mg is clear here, mg. Why? Because the mass is 3 and g is 10, so it's 30. There is more likely a dynamic friction, which is opposing that. And if I know that, I can write mg minus dynamic friction is equal to ma, the vertical acceleration. Okay, let's continue. Here the dynamic friction is supposed to be mu d times n. But what the normal force is, let's check. Actually, the surface, the wall, is vertical. So the horizontal force of n will cancel that 60. So normal force will be equal to the force we are holding the object on the wall. So n is going to be 60. Here, as you see, the normal force has nothing to do with the mg. Okay, this is the 60 Newton. Then I can start finding the dynamic friction. It is mu d times the normal force. Mu d is 0.2, so it's 0.2 times the normal force, which is 60, so it's easily 12. Okay, 12 Newton vertically upward and 30 Newton downward. So the net force in vertical direction will be 30 minus 12 is equal to ma. Mass of the object is given to be 3 and a is my goal. Okay, here I have 18 is equal to 3a, so acceleration is going to be 6 meters per second squared. Vertical acceleration, of course, downward. A box on a horizontal surface is pushed to a speed of 20 meters per second and then released. Calculate the braking distance and the braking time. Dynamic coefficient of friction is 0.5 and g is given to be 10. Okay, let's consider the question. Here, I push the object to a speed of 20 meters per second, and the question starts from here. Then I release the object. When I release the object will start after a few meters. So let's say it's x, the braking distance, and time, the braking time, the corresponding braking time. I'm looking for these two. I may have different kinematical approaches for x and t. One of them is maybe you can use like v is equal to negative at plus v naught. And the final velocity is 0 here when the object stops. So 0 is equal to negative a times t plus v naught, which is 20. If I have the acceleration, I can find the time, the braking time, and then I can find the x. But I know that this is the missing part. I should find the acceleration. To find the acceleration, I can't go for any kinematical approach. In dynamics, I should find the solution first. So first of all, I believe that there is always an opposing force like the friction, which is mu d times mg. You know that dynamic friction is mu d times n, but here the normal force is equal to mg. So instead of n, I can write mg. So it's mu d times mg. Is there any other force acting on the object on horizontal direction? I don't see any, because I release the object here. So there is no pushing force anymore. So on this direction, there is no force. So this is the only force acting on the object. If I write F net Newton's second law to be equal to ma, the F net is nothing but the dynamic friction. Good. So let's put it equal to ma. And acceleration necessarily is leftward. Okay, if I cancel the mass, I will have acceleration to be mu d times g. It's very good. So I have the acceleration now. Mu d is 0.5 and g is given to be 10. So acceleration is 5. Good. Now I can find the stopping time, the braking time, and braking distance. But a very easy approach will be the graph. Let's draw the Vt graph. The velocity at the beginning of the process when I release the object, at the beginning, the initial speed is v naught. Then the object will stop after a few seconds. So this is the braking time. And the area under the graph is the braking distance. You know, this is the delta x or x. Okay, so it's very easy. I will start from 20 and continue the line, the descending line, to cross the t-axis at this point. Okay, how to find this time is very easy. You know the acceleration is the slope of this graph, and the slope is 5. So in this right triangle, I believe that the slope is going to be vertical divided by horizontal. So it's 20 divided by t. Here it seems that t is 20 divided by 5. So it's 4 seconds. Very easy. So the stopping time, the braking time is 4. The area under the graph is the total distance traveled from the release to the stop. So it's going to be height 20 multiplied by the base 4 divided by 2. Okay, it is 40. So the object will travel for 40 meters and in 4 seconds, and it will stop here. That's all. We are done. Is the dynamic friction affected by the area of contact? The answer is no. If we keep the same nature of the surfaces, I mean the roughness and maybe the material, this wooden block will have the same friction even if you put it on a very large area of contact. No, it's not affected. The next question, is the coefficient of dynamic friction affected by contact force? In many textbooks, the introductory textbooks in high school, the answer is no. But indeed, yes, if you make the object with the same nature of surfaces in contact but heavier, yes, sometimes the mu d is affected. But for the time being, in high school, we usually ignore it and we say mu d is always the same. Okay, this is the end of video. Thank you for watching this video. Thank you for being with me. The next video will be about static friction. So let's go.